4 light-years away, closer than any other world we could hope to reach. A planet almost exactly the mass of Earth circles the nearest star to our Sun. We call it potentially habitable. We imagine oceans, weather, a second home. But here is the unsettling truth. We have never seen its surface. We do not know if it still has air, and the star beside it erupts with flares powerful enough to strip a sky away in seconds. Everything comforting about Proxima Centauri b is a hope. Everything hostile about it is physics. Tonight, we stand on that world under the scenarios science actually allows, and discover why arriving there would not mean finding a second Earth, only learning to survive beside a star that never promised to spare us. If you find yourself wondering what it would truly feel like to stand on another world, maybe consider tapping like and subscribing. It genuinely helps this channel grow. Now, settle in and get comfortable. Let's begin. Start with the number that makes everyone lean in. 4.2 light-years. That is roughly the distance to Proxima Centauri b, and in the vocabulary of the cosmos, that number sounds like an invitation. Every other star you have ever wished upon sits tens, hundreds, thousands of light-years away. This one does not. Proxima Centauri is the closest star to our Sun, and tucked against it is a planet with almost exactly the heft of the ground beneath your feet. Not a gas giant, not a scorched cinder the size of a small moon, a world that on paper weighs about what Earth weighs, sitting at a distance from its star where the temperature might allow liquid water to pool on solid rock. For a species that has spent its entire history staring upward and wondering if there is anywhere else to go, this is the closest thing to a door that the universe has ever offered us. And so the imagination runs ahead of the evidence. We picture coastlines, we picture rain, we picture a place where a human being could one day stand outside, look up, and call it home. The phrase attached to this planet in nearly every headline is potentially habitable, and the human ear tends to hear only the second word. Habitable, livable, a second Earth, waiting 4.2 light-years away for us to grow up enough to reach it. Hold on to that image, because this entire story is about the distance between that image and what the science actually permits, not the distance in light-years, the distance between what we hope is true and what we have genuinely measured. Because here is the first uncomfortable fact, the one that reframes everything that follows. No human eye, and no telescope ever built, has seen the surface of Proxima Centauri b. We have never photographed it. We have never watched it cross the face of its star. We do not know what color it is. We do not know if it has air. Almost everything you have ever been told about this world is not an observation. It is an inference, a model, or a hope wearing the costume of a fact. To understand why, you have to understand the star it orbits, because the star is the entire context of this planet's existence. Proxima Centauri is a red dwarf, and red dwarfs are nothing like our Sun. Our star is a warm, yellow middleweight furnace. Proxima is a dim ember by comparison. It carries only about 12% of the Sun's mass, and it burns with less than 1/5 of 1% of the Sun's brightness. Its surface glows at roughly 3000 Kelvin, far cooler than our star, which means most of the light it pours into space is not the crisp white we see from the Sun. It is deep red, sliding into the infrared, into wavelengths your eyes can barely register or cannot register at all. If you swapped our Sun for Proxima, the daytime sky of Earth would go dark and bloody, and every green plant that ever evolved would begin to starve. A star this feeble has a strange and important consequence. To be warm enough for liquid water, a planet cannot sit out where Earth sits. It has to huddle in close, extremely close, pressed right up against the dying warmth of the ember, and that is exactly where Proxima Centauri b is. Picture the whole geometry like standing near a campfire on a freezing night. Our Sun is a roaring bonfire, and Earth stands a comfortable distance back, warmed but not burned. Proxima is a single guttering candle, and to feel any heat at all, its planet has to lean in until its face is almost touching the flame. Proxima b completes an entire orbit, an entire year, in about 11.2 Earth days. Take that in again. A year on this world is shorter than a fortnight on ours. It circles its star at roughly 1/20th of the distance between Earth and the Sun. Its entire orbit would fit comfortably inside the orbit of Mercury, with room to spare. This is a planet living inside its star's personal space, and that single fact, the intimacy of that orbit, will turn out to shape every hour of any life that might exist there. So, how do we know any of this, if we have never seen the planet? This is where the story gets honest about its own limits. Proxima b was announced to the world in 2016, the crowning result of a patient campaign that watched this one dim star night after night. But the astronomers were not looking at the planet. They could not. They were looking at the star, and they were watching it wobble. Here is the trick, and it is a beautiful one. A planet does not simply orbit a fixed, stationary star. The planet and the star both circle their shared centre of mass. Like two dancers holding hands and spinning, the small partner swings wide, and the large partner rocks in a tight little circle in response. As Proxima b swings around, its gravity tugs the star very slightly toward us and then very slightly away from us, over and over, on a strict 11.2-day rhythm. That motion stretches and compresses the starlight by an almost imperceptible amount, shifting its colour toward the blue as the star approaches and toward the red as it recedes. Astronomers measured that rhythmic shimmer in the light and worked backward to the thing causing it. They never saw the dancer. They inferred the dancer entirely from the way its partner rocked, and getting even that much took a campaign of almost monastic patience, because a wobble this small does not simply announce itself. In the early months of 2016, a team of astronomers pointed a spectrograph called HARPS, an instrument built to measure the colour of starlight, with almost absurd precision at Proxima night after clear night from a mountaintop in Chile. In a dedicated hunt, they gave the poetic name Pale Red Dot. For roughly 2 months they watched this one dim star, taking its pulse, measuring the faint back and forth shiver in its light, looking for a rhythm hidden inside the noise. That is the part worth sitting with. The rhythm was hidden inside noise, and the noise came from the star itself. Because Proxima is not a calm, obedient lamp that holds still while we measure it. It is an active, spotted, flaring red dwarf, and its surface churns. It is mottled with enormous star spots, dark, cooler blotches that rotate into and out of view as the star slowly turns, once about every 83 days. And here is the cruel trick those spots play. As a dark spot rotates across the face of the star, it distorts the star's light in a way that can imitate the very wobble a planet produces. The star's own restlessness generates false signals, phantom rhythms that can drown out or even mimic the tug of an orbiting world. So the astronomers were not simply listening for a drumbeat in a silent room. They were trying to pick out one steady, 11.2-day drumbeat buried under the crackle and hiss of a star that will not stop fidgeting, separating the heartbeat of a planet from the twitching of the body it orbits. That is why hints of this planet had floated in earlier data for years, without anyone being willing to plant a flag. The signal was there, but proving it was the planet and not the star's own activity took the focused pale red dot campaign to nail down, and then took still more years of follow-up observations by separate teams using separate instruments to confirm beyond reasonable doubt. Only after all of that cross-checking did Proxima b graduate from tantalizing signal to confirmed planet. I want you to hold that in mind whenever anyone speaks about this world too confidently, because it tells you how hard won even the certainties are. The single thing we are most sure of about Proxima b, that it exists at all, required us to first understand and subtract away the tantrums of its star. Everything past that first hard fact is built on far shakier ground, and notice the quiet irony sitting inside this. The same restless magnetic violence that nearly hid the planet from us in the data, the flaring, the spots, the churn, is not a mere inconvenience for astronomers. It is, as we will see, the central threat to whether anything could ever live on the world it concealed. The star fought us for the discovery, and it may yet be fighting the planet for its very sky. But that is a danger for later. For now, simply register what it took to read those footprints in the starlight. Not a glance, but years of staring at a moving target through the smoke. The target itself was throwing up. The detection is real. It is also, in the most literal sense, a triumph over interference, and it left us knowing the planet's orbit far better than we know the planet. This method is powerful, and the detection is solid. The planet is real, confirmed by years of careful measurement. But you must understand what this technique can and cannot deliver, because the gaps are the whole point. Reading a planet from its star's wobble is like being a detective who arrives after the intruder is long gone and finds only a single line of footprints pressed into snow. The footprints are undeniable. Someone was here. From their spacing, you can estimate a stride. From their depth, a rough weight. But you never saw the person. You do not know their face, their height, their build. You are reconstructing a whole individual from the marks they left in something soft. That is precisely our relationship with Proxima b. We are reading a set of footprints in starlight. So let us be disciplined and sort what those footprints actually tell us into tiers, because this sorting is the honest map of our ignorance. Start with the first tier. The things we have genuinely measured. We have measured the orbital period with real confidence, about 11.2 days. From that period and the mass of the star, we can calculate the size of the orbit that close, roughly 1/20th of the Earth-Sun distance. And because we know how bright Proxima is, we can calculate how much starlight actually falls on the planet. The answer is about 65% of the sunlight that reaches Earth. Not a trivial amount. Not a frozen exile flung to the edge of the system. A genuinely temperate dose of energy, right in the range where, in principle, water could be liquid rather than ice or vapor. These numbers are the firm ground of the whole story, and they are genuinely exciting. They are why anyone cares about this planet at all. But watch what happens when we reach for the next number, the one everybody actually wants. How heavy is it? How big is it? What is it made of? Here the footprints go blurry. The wobble technique does not measure a planet's true mass. It measures something slipperier, the minimum possible mass. This is one of the most misunderstood facts in all of exoplanet science. So let me make it concrete. The size of the star's wobble depends not only on the planet's mass, but also on the angle at which we happen to be viewing the orbit. If we are looking at the orbit edge on, we see the full back and forth motion, and our mass estimate is accurate. But if the orbit is tilted, we only catch part of that motion, and the true mass is larger than it appears, sometimes much larger. We are seeing a silhouette. A silhouette gives you a shape's outline but hides its depth. A person's shadow on a wall tells you they are at least so tall, but they could be standing sideways, far broader than the shadow admits. The measured minimum mass of Proxima b is just over 1 Earth mass, around 1.1, and by some estimates as much as 1.3 when the arithmetic is done a certain way. But that is a flaw, not a value. The planet is at least that heavy. It could be heavier. We do not know the tilt of the orbit, so we do not know the true number. And that single uncertainty cascades into a much larger blindness because of one cruel accident of geometry. Proxima b does not transit its star. From our vantage point, the planet never passes directly in front of Proxima and dims its light, the way some other worlds obligingly do. The odds of such a crossing being visible from Earth were only about 1.5%, and we appear to have lost that particular lottery. This matters enormously, because a transit is how astronomers measure a planet's physical size, its radius. No transit means no measured radius. And here is the chain reaction. If you do not know the true mass, and you do not know the radius, then you cannot calculate the density. And density is the single most important clue to what a planet actually is. Density is how you tell a ball of rock from a puffed-up envelope of gas from a deep world of water. Without it, the most basic question is this even a solid, rocky planet you could stand on, or something else entirely is not measured. It is assumed. There is one more thing the wobble revealed, and it turns out to matter enormously for everything that follows. Proxima b does not orbit alone. This little red star holds at least a small family of worlds. Closer to the star than Proxima b, whipping around in a mere 5 days or so, sits a second confirmed planet. Proxima d, a feather of a world, heavier than Mars but only about 1/4 of Earth's mass, one of the lightest planets ever detected by the wobble method at all. And further out, on a far wider and slower orbit lasting something like 5 years, lurks a third heavier candidate, Proxima c, a world several times the mass of Earth, still not fully confirmed, still argued over, but repeatedly showing up in the data. So the picture is not a lone planet against a star. It is a system, a tight little household of worlds circling the nearest ember to our Sun, with Proxima b sitting in the temperate middle. Now, why should the existence of a Mars mass runt on a 5-day orbit, or a disputed heavier world far outside, have anything to do with what it would feel like to stand on Proxima b? Because planets do not ignore one another. They pull every time these worlds swing past each other in their orbits. They exchange faint gravitational tugs, and over millions of years those repeated nudges can do something crucial. They can keep Proxima b's orbit from settling into a perfect circle. Left utterly alone, a planet gripped this tightly by its star would tend, over time, to have its orbit rounded off and smoothed into a near-perfect ring. But a planet with siblings gets jostled. Its orbit can be kept slightly stretched, slightly eccentric, pumped over and over by the gravity of its neighbours. Hold on to that word, eccentricity, the stretch of the orbit, because that single unmeasured quantity is the master dial for almost everything strange we're about to encounter. Remember from the very close orbit that Proxima b is almost certainly locked in some deep tidal grip, but exactly which grip depends entirely on how stretched its orbit is. A nearly circular orbit and a stretched one would settle the planet into entirely different rhythms of spin, and with them, entirely different skies, entirely different patterns of day and night, which we will step into for ourselves in just a moment. And that same unmeasured stretch would reach deeper than the sky alone. It would help decide how much the planet is flexed and heated from within, and even whether it can cling to its air questions we will not be able to escape later. The family, in other words, may quietly decide whether the sun in Proxima b's sky stands still forever or crawls in slow, strange arcs. And the same dial, as we will find, does more than set the sky's clock. A stretched orbit means the planet is being flexed and kneaded by tides as it swings nearer to and farther from the star, and that flexing generates heat deep inside the world, heat that could stir volcanoes, and volcanoes that could breathe gas back into a dying atmosphere. So the presence of these sibling worlds, detected as nothing more than extra whispers in the star's wobble, reaches forward into questions of daylight, of climate, and of whether the planet can even hold on to its air. We have not measured the eccentricity. We cannot yet read the dial. But we now know the hand that turns it a household of unseen worlds, and we know that where that dial points may matter more to a future settler's daily life than almost anything else we could name. So slide down into the second tier, the things we reasonably infer but have not directly seen. We infer that Proxima b is probably rocky, because a world of roughly 1 Earth mass, if it is made of ordinary planetary stuff, is most naturally a rocky body rather than a gas giant. That is a sensible bet, grounded in everything we know about how planets of this weight tend to form. But it is a bet, riding on a mass we only know as a minimum. We also infer a temperature. You will often see Proxima b assigned an equilibrium temperature of about -39 degrees Celsius, a hard Antarctic cold, but that number describes a bare, airless rock with no atmosphere to trap heat, spinning in the planet's share of starlight. It is a baseline calculation, not a measured surface reading. Give that same rock an atmosphere, and the real surface temperature could climb dramatically. A thick blanket of gas could warm it well above freezing, exactly the way our own atmosphere keeps Earth from being a frozen wasteland. So even the temperature you have heard quoted is not the temperature of the ground. It is the temperature of an idealized rock in a model, before the single most important variable, the air, is even allowed into the equation. Which brings us, finally, to the third tier, and this is the tier that should change how you think about this planet forever. This is the list of things we simply do not know. Not know imprecisely. Do not know at all. We do not know if Proxima b has an atmosphere. That is not a detail. That is the whole question of whether it is a world or a rock, and it is completely open. We do not know if there is any water on its surface, or beneath it, or anywhere. We do not know whether it has a magnetic field to shield it. We do not know how it spins. We do not know whether its skies are clear or clouded, whether it has ever had oceans, whether it lost them, whether it kept them. Every one of those unknowns is not a missing decimal place. Each is a fork in the road that leads to a completely different planet. Sit with how strange that is. We have a world we can name, whose year we can time to the day, whose distance we can state to a fraction of a light year, and we cannot answer the most childlike question you could ask about it. What is it like there? The map we have drawn of Proxima b has a precise dot marking where it is, a precise clock ticking out its orbit, and then, across the entire region where the surface should be, a vast blank space. Here be dragons, or here be oceans, or here be nothing but sterilized stone. The map does not say, because we have not been able to look. And this is exactly where the most seductive phrase in the whole story starts to unravel that comforting label, habitable zone. It is a real and useful idea, but the human ear systematically misunderstands it. The habitable zone is not a region where planets are habitable. It is defined much more modestly and much more coldly. It is the band of distances around a star where the starlight is neither so strong that any water would boil away, nor so weak that all water would freeze solid. That is the entire definition. It is a statement about the intensity of the light falling on a world, and nothing more. Being inside the habitable zone means a planet receives the right amount of warmth to permit liquid water on its surface if that surface exists, and if it holds water, and if it has an atmosphere to keep that water from flashing straight into space, and if a dozen other conditions are met. The habitable zone describes the delivery of heat. It does not describe air, or oceans, or shelter, or life. It is a porch light left on at the right brightness. It says nothing about whether anyone can live in the house, or whether there is a house there at all. So when you hear that Proxima Centauri b sits squarely in the habitable zone of the nearest star, hear it correctly. It means the planet is standing at the right distance from the campfire to be warmed rather than frozen or scorched. It is a genuine and remarkable thing to be able to say about the closest planet beyond our own solar system. But it is a statement about a location, not a verdict about a home. The word habitable in that phrase is doing an enormous amount of quiet, unearned work, and once you notice it, you cannot unnotice it. And there is one more shadow falling across even this cautious optimism, a shadow we have so far kept in the corner of the frame, the star. That same dim ember whose faintness forces the planet to huddle so close is not a gentle, steady candle. Red dwarfs like Proxima are famous for their violence. They convulse, they flare. This small, cool star is capable of erupting without warning into bursts of radiation that can briefly outshine its normal output many times over, hurling ultraviolet light, X-rays, and streams of charged particles directly at the planet pinned so tightly in its orbit. We will spend much of this journey reckoning with what that means, because it may be the single most decisive fact about whether anything could survive there. For now, simply hold the tension in place. The very intimacy that lets this world stay warm also drags it into the firing line of a temperamental star. The warmth and the danger come from the same place. They cannot be separated. Standing at the edge of the blank space on the map, we have a planet that is real, confirmed, and astonishingly close. We know its orbit, its year, and the dose of light it drinks. We suspect it is rocky and roughly Earth-massed. And beyond that, we are almost entirely in the dark. No measured size, no measured density, no confirmed air, no confirmed water, no known spin, no known shield, orbiting a star prone to fits of fury. The honest picture is not a second Earth. It is a silhouette in starlight, sitting at the right distance from a candle, wrapped in questions. But a blank map is an invitation, not a dead end, because within everything we do not know, the laws of physics still hold. The models can still be run. We can still ask, carefully and specifically, given what is genuinely possible, what would it actually be like to stand on that ground and look up? What would that swollen red star look like frozen in the sky? How long would the day last, or would there be no day at all? What would time itself feel like on a world whose year ends before your ice would melt? The measurements have taken us as far as they can. Now we step past the edge of the data, onto the surface itself, into the strange and specific reality of standing beneath a red sun that never moves. Step off the edge of the map with me, but step carefully, because the moment we set a boot on the surface of Proxima Centauri b, we are making an assumption, and I want it named out loud before we take another step. To stand on this world and look up, we have to assume there is a solid surface to stand on, and enough of an atmosphere above it to hold a sky. Neither of those is confirmed. We are choosing a scenario, a rocky planet with at least some air, not because we have proven it, but because it is the only way to ask the next honest question. If this world is roughly what we hope it is, what would it actually be like to be there? Hold that "if" in your hand the whole time. Do not put it down. Everything that follows is an experience built on a premise we have not yet verified. Now, look up. The first thing that would stop your breath is the sun. Not our sun Proxima, that dim red ember we met at the outset. The star so faint it forces its planet to huddle close. From the surface of Proxima b, that faintness does something your intuition will fight. Because the planet orbits so tightly, the star does not appear as a small bright disk the way our sun does from Earth. It looms. It hangs in the sky roughly 2.5 times as wide as our sun looks from home. A vast, swollen circle of deep red light covering several times the area you are used to seeing. If you have ever watched a fat red sun sink into the horizon on a hazy evening and thought it looked unnaturally large, imagine that bloated disk lifted to the top of the sky and left there. That is the scale of the thing you would be living under. And yet here is the paradox that defines this whole sky. It would not be bright. This is the strangest part to hold in your mind. The star is enormous in the sky, but it is dim. Proxima pours out only a fraction of the sun's energy, and even huddled this close, the planet drinks only about 2/3 of the light that Earth gets. So the disk is huge, but the light is thin. Picture a dying coal the size of a dinner plate held up against the sky. Broad, close, glowing but not blinding. The daylight on Proxima b, if you stood in the open, would feel perpetually like the last half hour before sunset on Earth. A ruddy, low, amber dimness that never brightens into true day and never quite fails into true night. A permanent dusk, lit by a red giant of a disk that is really just a small, cool star worn very close to the skin. The colour would change everything about how the world looked. Our sun burns white hot, spilling out the full rainbow, which is why Earth's daylight is crisp and its plants are green. Green leaves are green precisely because they are drinking the red and blue light our star provides so generously. Proxima is far cooler, around 3000 Kelvin at its surface, and a cooler star pours most of its energy into the red end of the spectrum and beyond, into the infrared, into wavelengths your eyes cannot see at all. So a huge fraction of the energy warming Proxima b is invisible heat, felt but not seen. The light you could see would be reddened, drained of blue, the whole landscape washed in the tones of a fire burning low. Rocks that would look grey on Earth would look rust and umber here. Any shadow would be soft and dark and long, because the light source, though wide, is weak. It would be a world lit the colour of embers, and it would stay that colour forever. But the red sun is not the only thing burning in that sky, and the second sight would be, in its own way, just as astonishing. Because Proxima Centauri is not a solitary star. It is the outermost, loneliest member of a family of 3, slowly circling over something like 500,000 years, a pair of far grander stars, Alpha Centauri A and B, one a near twin of our own sun, the other a slightly smaller, more orange companion, and that pair is close. Not close the way the planets in Proxima's own household are close, but close on the scale of the stars only about 1/5 of a light year away, which in stellar terms is practically arm's reach. It means that in the sky of Proxima b, Alpha Centauri A and B would not be 2 anonymous dots lost among the constellations. They would blaze. Try to picture it. Turn away from the swollen red disk of the local star and look into the dark, and there, hanging together as a close and dazzling pair, would be 2 brilliant golden white points, far brighter than any star that has ever graced Earth's night, brighter, in fact, than Venus at its most radiant. 2 burning jewels, one warm and yellow like a distant echo of the sun that made us, the other a shade more orange, sitting side by side in the black. They would be bright enough, together, to be the most luminous things in the entire sky after Proxima itself. Bright enough, quite possibly, to cast their own faint doubled shadows across the ground on the night hemisphere. Bright enough, perhaps, to still be glimpsed as fierce sparks even against the dim red glow of full daylight. And yet this is the crucial restraint: they would not be suns. They are still 1/5 of a light year away. They would remain points, not disks, brilliant beyond anything in our sky, but pinpricks of light, not a second source of warmth. They would give Proxima B dazzling stars, not a second day. On human timescales, those two jewels would hang essentially fixed, a permanent double beacon in the heavens, wheeling only with the planet's own rotation. Over hundreds of thousands of years they would drift as Proxima swings around them, but no settler, no dynasty of settlers would ever see them move. They would simply be there, the way a mountain is there, the brightest, steadiest ornament of an alien night. Two suns that are not your sun, close enough to blaze and far enough to be useless for warmth. And then, if you knew exactly where to look, there would be one more sight in that sky, and it is the one that ought to stop a human heart. Somewhere in that scattering of stars, in the direction of the constellation we call Cassiopeia, there would be a single yellow star, indistinguishable from a dozen others. Not the brightest thing in that sky, not the faintest, nothing at all to mark it out. The kind of star you would need a companion to point out to you. That anonymous point would be the sun. Our sun. The star that lit every sunrise in human history, that grew every field, that warmed every ocean our species has ever sailed, reduced. From the surface of Proxima B to a single pale point you could hide behind a fingertip. From the nearest potentially habitable world to Earth, the entire solar system, the sun and all its planets, everything that has ever happened to anyone, collapses into one faint star in an alien constellation. Not the center of anything, just another light in someone else's sky. I will let that image sit rather than lean on it, because there is a colder practical fact hiding inside the wonder, and it belongs to this part of the story about light and sky. Those two brilliant companion stars, and that faint yellow speck, would give the night hemisphere of Proxima B a sky of real and startling beauty, but they would not lift its darkness in any useful way. Under permanent night, with only distant stars for light, the far side of this world would stay locked in a cold, dim gloom that no amount of stellar beauty could warm or brighten into anything a human would call day. The sky would be spectacular. The ground beneath it would still be freezing in the dark, which returns us, unavoidably, to the question the sky keeps forcing on us, not how lovely the light is, but where it falls, and where it never does, and what that does to a world. That reddening is not just a matter of scenery. It reaches all the way down into the question of whether green life, as we know it, could even feed itself here. On Earth, photosynthesis is tuned to the light our sun provides, and it leans heavily on exactly the visible red and blue wavelengths that Proxima produces so little of. A plant transplanted to the surface of Proxima B, assuming, again, an atmosphere and liquid water, which we have not confirmed would find itself starved of the specific light it evolved to eat, drowning instead in infrared it cannot use. This does not mean life is impossible. It means Earth's particular solution to living off starlight might simply not work here. Perhaps a different biology, evolved on this world or engineered by settlers, could learn to harvest the deep red and near-infrared glow. But notice the tears of that claim. That Earth plants would struggle is grounded physics. That some other photosynthesis could thrive on infrared is speculation. Keep them separate. The honest picture is a dim red garden where nothing familiar grows easily. And what colour would the sky itself be? On Earth, the sky is blue because our air scatters blue light most strongly, painting the whole dome. But that scattering is weakest for red light, and Proxima's light is mostly red. Combine that with a thinner or differently composed atmosphere, if there is one, and the sky above you might not be blue at all. It might be a dim, dusty rose or a deep ochre, or nearly colourless and dark with the great red disk of the star burning through it. This is genuinely uncertain, because the sky's colour depends entirely on an atmosphere we have not measured. But it is a fair thing to say that a human standing on Proxima B would almost certainly not look up into a blue sky and white sun. The palette of an entire world would be shifted toward the red, permanently. Now, and this is where the true strangeness begins, watch what the star does. Or rather, watch what it does not do. On Earth, the defining rhythm of existence is the sun's march across the sky. It rises, it climbs, it crosses, it sinks, it sets. That arc is the metronome every living thing on our planet is built around. It gives us morning and noon and evening and midnight. It is so fundamental that we forget it is a feature and not a law of the universe. On Proxima Centauri b, in one of the leading scenarios for how this planet spins, that arc simply does not happen. The sun would rise once and then never move again. This is the scenario astronomers call synchronous rotation, or tidal locking, and it flows directly from that intimate orbit. A planet pressed this close to its star is gripped by enormous tidal forces, the same kind of gravitational tug that keeps our moon showing only one face to Earth. Over time, those forces can slow a planet's spin until it turns exactly once for every orbit, a one-to-one match between its day and its year. And when a planet's day equals its year, something profound happens to its sky. The star stops moving. One hemisphere is left facing the star forever, and the other is turned away into permanent dark, and the change from one to the other never comes. There is no sunrise, there is no sunset. There is no tomorrow in the sense you mean it, because there is no night to separate today from the next day. Time still passes. The clock of the 11.2-day orbit still ticks, but the sky holds its breath and does not turn. Try to actually inhabit that. Where you happen to stand on this world would not just be your address, it would be your entire relationship with light, permanently, for the rest of your life. Stand at the very center of the star-facing hemisphere, the point astronomers call the substellar point, and the red disk hangs directly overhead, motionless, at the top of the sky, like a spotlight bolted to a ceiling that will never be switched off. Eternal high noon. The sun never climbs because it is already as high as it will ever be, and it never falls because nothing here falls. Walk in any direction, for hundreds or thousands of miles, and you would see that overhead sun slowly sink toward the horizon behind you, not because it is moving, but because you are curving around the body of the planet. Keep walking, and eventually you would reach a place where the great red disk sits permanently on the horizon, half risen, half set, frozen in the act of dawn that never completes. This is the Terminator, the ring of eternal twilight that wraps all the way around the world, dividing the endless day from the endless night. And keep walking past it, onto the far hemisphere, and the star would slip below the horizon behind you and never return. You would be in permanent darkness, under a sky that has never once, in the planet's entire history, shown the sun. So a tidally locked Proxima b would be, in the most literal sense, an eyeball of a world. Picture it from space. A bright, warm pupil of eternal daylight, staring perpetually at its star, ringed by a dim iris of perpetual twilight, wrapped in an outer darkness of eternal night. Where you live on that eyeball would define everything, whether you exist in changeless glare, changeless dusk, or changeless black. There would be no shared sunrise, no dawn chorus, no evening. The very words day and night would stop being events that happen to everyone and become places you either live in or you do not. There is a further consequence of that frozen sun that almost no one imagines when they picture living in the gentle twilight ring, and it is this. On a tidally locked Proxima b with any real atmosphere, the air itself would never hold still. It would blow, hard, forever, in a wind with no season and no end. The reason is simple and relentless. On the day side, the motionless star pours heat onto one patch of the world without pause, warming the air there until it swells and rises. On the night side, the air sits in perpetual dark and cold, dense and sinking. And nature abhors that imbalance. Warm air lifting off the day side has to go somewhere, so it streams outward, up and over the Terminator, spilling toward the cold night hemisphere, while cold air comes flooding back along the surface underneath to take its place. This is not weather that comes and goes. It is a single, planet-wide circulation locked permanently in place by a sun that never moves, a river of air flowing eternally from the hot face of the world toward the cold one, driven by a temperature difference that can never resolve because the light never shifts. Stand at the Terminator, then that ring of everlasting dusk that so many people picture as the mild, comfortable place to build a home, the balmy border between too hot and too cold, and you would not find calm. You would find yourself standing in a doorway between a furnace room and a freezer, where the draft howling through the gap never once dies down. The winds funneling across that twilight boundary could be ferocious and unceasing. a gale you would lean into on your way to work and lean into again on your way back, blowing from the same direction it blew yesterday and last year and 10,000 years before you were born. Climate models of worlds like this routinely produce not just these day-to-night flows, but great planet-circling jets of wind, whole bands of atmosphere racing around the globe because a permanently uneven world drives permanently organized air. So the tidy fantasy of the habitable ring the idea that even if the day side bakes and the night side freezes, a person could simply settle in the comfortable strip of dusk between them runs straight into a wall of moving air. The twilight zone might well be the most temperate band on the planet. It might also be one of the windiest places imaginable, scoured by a permanent gale, its skies streaked with cloud dragged in from the day side, its temperature swinging sharply over short distances as you moved even a little toward the heat or a little toward the dark. It would not be a gentle porch between two extremes. It would be the seam where two extremes grind against each other, and the wind would be the sound of that grinding. I raise this here while we are still taking in what you would see and feel, because the wind is something you would feel in your body from the first moment before you ever thought about atmospheric chemistry or heat budgets. You would notice that the air on this world moves with a purpose and never stops. But that same wind is also a promise of something deeper, something we cannot answer just by standing here and squinting at the sky. Because whether that endless wind is a survivable breeze or a killing storm, and whether it carries enough warmth from the day side to make the night side livable at all, depends entirely on how much air there is to move and what that air is made of. And that, at last, is the question we can no longer put off. Not where the light falls, but whether this world has a sky worth the name. But I have been slightly too clean, and honesty demands the complication. Even a tidally locked star would probably not sit perfectly still, because Proxima B's orbit may not be a perfect circle. It may be slightly stretched, slightly eccentric. The planet would speed up and slow down as it swung closer to and farther from the star across each 11.2-day loop. Its spin, though, would stay steady, and when a steady spin is paired with a varying orbital speed, the star appears to rock. Over the course of the orbit, that overhead sun would nod back and forth and swell and shrink a little as the planet drew nearer and pulled away, tracing a slow, small figure in the sky and returning to where it began. It would be less like a fixed lamp and more like a sundial whose gnomon has come loose and sways gently in place, never marching across the sky, but never perfectly still either, breathing out the rhythm of the orbit. It is a subtle motion, but on a world where the sun is otherwise frozen, that gentle rocking might be the only clock the sky ever offers. Now change the scenario, because we owe it to the evidence to admit we do not actually know how this planet spins. Tidal locking is the most likely outcome, but it is not the only one. If Proxima B's orbit is stretched enough, if its eccentricity climbs past a modest threshold, the planet might have been captured instead into a different rhythm, the same one our own Mercury fell into. A 3-to-2 resonance, 3 turns of the planet for every 2 trips around the star, and a 3-to-2 world is a completely different experience of time, because now the sun does move, but it moves in a way no human sky has ever shown. On a 3-to-2 Proxima B, there would be a day and a night, but a single day from one high noon to the next high noon would not last 11.2 days. It would last you about 22 of our days, because the planet's slow spin and its orbital motion partly cancel, stretching the interval between noons to roughly 2 full orbits. So you would live through something like 11 Earth days of continuous daylight, followed by 11 Earth days of continuous darkness. Over and over, a light and dark cycle nearly a month long. The red sun would crawl across the sky so slowly that its motion would be almost imperceptible hour to hour, a disk that takes weeks to cross from horizon to horizon. And because the orbit is eccentric, the star would not crawl at a constant pace. As the planet raced through the closest part of its orbit, the star's apparent motion across the sky could actually slow, stop, and briefly reverse. The sun would rise part way, halt, back down toward the horizon it came from, then turn around and resume its crawl. Mercury does exactly this. From parts of its surface you could watch the sun rise, sink back, and rise a second time. On a 3-to-2 Proxima B, a sunrise might be a thing that happens twice, days apart, with a false dusk wedged between. Whole generations of settlers might structure their lives around a solar day longer than an Earth month, a rhythm no human body has ever known. And if the orbit is more stretched still, an even more extreme resonance becomes possible: 2 turns for every one orbit, or others, each one producing its own bizarre choreography of a slow red sun lurching unevenly across a reddened sky. The point is not to memorize the options. The point is that we do not know which one is real, and every option is profoundly alien. On Earth, the length of a day is a fixed, comfortable 24 hours, the same everywhere, the same always. On Proxima b, the length of a day is not merely different, it is unknown, and every candidate answer is stranger than the last. The sky might never turn, or it might turn once a month, or it might turn and stutter and turn back. We simply cannot yet say. Layer onto this the matter of seasons, and the alien clock gets stranger still. On Earth, seasons come from the tilt of our axis, the way we lean toward and away from the sun through the year, giving us summer and winter. But a planet worked over by tides for billions of years tends to have that tilt erased, its axis pulled nearly upright. If Proxima b stands upright, as it probably does, then it has no axial seasons at all. There is no summer, no winter, no long swing of warming and cooling across the year, at least not from tilt. Whatever seasonal rhythm exists would come instead from the orbit's own stretch. As the planet swung closer to the star and then farther away across each 11.2-day loop, the intensity of light and heat would rise and fall. So the only seasons might be a fast pulse of stronger and weaker starlight cycling once every 11-day orbit a year, and a season collapsed into the same brief span, beating far faster than any rhythm life on Earth has ever had to track. Sit for a moment with what all of this would do to a human being living there, because we are so shaped by our sky that we barely notice it. Every cell in your body runs on a roughly 24-hour clock, a circadian rhythm calibrated over billions of years to the turning of the Earth. Sleep, hunger, temperature, hormones, mood, all of it is tuned to the daily rise and fall of the sun. Now put that body on the substellar point of a tidally locked world, where the sun never sets and the light never changes. There is no external cue to tell your body when to sleep, when to wake, when a day has ended, because no day ever ends. Or put that same body in the eternal night of the far hemisphere, where the sun never rises at all, and the darkness is total and unbroken. Or set it down on a 3-2 world, and ask it to live by a day that lasts a month, sleeping through a week and a half of darkness and waking to a week and a half of unmoving red light. The human clock has no setting for any of this. Settlers would have to build their time out of machinery, artificial lights, cycling on schedules, clocks and calendars imposed by engineering rather than read from the sky, because the sky itself would refuse to keep human time. On Proxima b, the day would not be something the world gives you. It would be something you have to manufacture and defend. Even the simple act of finding your way would be transformed. On Earth, the sun rises in the east and sets in the west, and that daily arc is a compass built into the sky. We have navigated by it for as long as there have been people. On a tidally locked Proxima b, there is no east and no west in that sense, because the sun does not travel, but there would be a different, absolute compass, one no other world offers. The star itself would be a fixed landmark burning in one unchanging patch of sky. To walk toward the star is to walk toward the heat and the eternal day. To walk away from it is to walk toward the twilight ring and then into the dark. You would never be lost as long as you could see the sky, because the sun would always tell you exactly which way the day was. It would be the stillest, most reliable landmark imaginable, a red beacon nailed to one spot in the heavens, marking the center of the world's lit face. Direction, on this world, would mean your relationship to a sun that never moves. And here is the thing I have been holding back, the thread that pulls us straight into what comes next. Everything I have just described, the frozen sun, the eternal noon, the twilight ring, the reddened sky, the strange stretched clock of the 3-2 world, all of it is about light. About where the warmth falls and where it does not. But light falling on a world is not the same as a world you could survive on. I have shown you an eyeball of illumination, a bright dayside pupil, and a black night side, and it is tempting to leap to the obvious conclusion that the dayside is a scorched hell and the night side a frozen tomb, with only a thin, habitable ring of twilight between them where a person could stand, resist that leap. Because whether that eternal noon hemisphere is a furnace or a mild, sunlit country, and whether that endless night is a solid block of frozen air or a survivable, wind-warmed dark does not depend on the light at all. It depends on something the light cannot tell you, whether this world has an atmosphere thick enough and oceans deep enough to pick up the heat piling up on the dayside and carry it around the globe to the night. A bare rock with no air would indeed bake on one side and freeze on the other, but give that same rock a real atmosphere, and the winds and currents could smear the heat across the whole planet, softening the furnace and warming the tomb, until the difference between eternal day and eternal night is far gentler than you would ever guess from the sky. So the eyeball we have been standing on is not yet a verdict, it is a question. The sun hangs frozen overhead, red and swollen and dim, but the fate of everyone beneath it rides entirely on the air, and the air is exactly what we turn to next. The great branching set of possibilities for Proxima B's atmosphere and climate. The scenarios that decide whether this world is a frozen stone, a temperate refuge, a storm-racked ocean, or a planet that lost its sky long ago and never got it back. We were just standing on an eyeball, a frozen red sun overhead, a bright pupil of eternal day, a ring of twilight, an outer dark of eternal night. And I asked you not to leap to the obvious conclusion that the day side is a furnace and the night side a tomb, with only a thin, habitable ring between. I asked you to resist that, because the light falling on a world does not decide the world. The air does, and the air is the one thing we turn to now, because everything, whether this planet is a scorched stone, a temperate refuge, a drowned storm world, or a corpse that lost its sky billions of years ago, hangs on a single question we cannot yet answer. Does Proxima Centauri b have an atmosphere at all? And if it does, how much, and made of what? So before we sort the possible worlds, we have to sit inside the possibility that there is no world to sort, that the sky is already gone. Here is why that is not pessimism but physics. Remember what kind of star this is. Proxima is a red dwarf, and red dwarfs have a cruel biography. They are born furious. When Proxima was young, before it settled into the slow, dim, stable burn it maintains today, it went through a long and luminous adolescence, a phase astronomers call the pre-main sequence, during which the star was far brighter and far hotter than it is now, and stayed that way not for a few years but for something on the order of 100 million years or more. And during that entire extended tantrum, Proxima b was already there, pinned in its tight little orbit, drinking in a flood of light and radiation many times more intense than it receives today. Think about what that does to a young planet. Whatever water Proxima b was born with oceans, ice, vapour, whatever inventory it started with would have been sitting under a star bright enough to boil it. Climate models suggest the planet may have spent that long adolescence in a runaway greenhouse, its water not lying calm on the surface but hanging in the sky as steam, exposed at the top of the atmosphere to the star's harsh ultraviolet and X-ray output. The reason the water climbed so high is a spiral that feeds on itself. As the young star's heat warmed the surface, the oceans began to evaporate, and water vapour is itself a potent greenhouse gas. So the more that rose, the more heat it trapped, which warmed the surface further and drove still more evaporation. Round and round the feedback turned, until the seas were not merely steaming but being hoisted wholesale into the upper air, filling heights that on a cooler world would stay bone dry. Only once the water was lifted that high did the real destruction begin. And up there, at the roof of the air, high-energy starlight is a knife. It splits water molecules apart into hydrogen and oxygen, and the hydrogen light, fast, hard to hold, escapes into space, dragging the planet's water away molecule by molecule over tens of millions of years. By some estimates, Proxima b could have lost an entire ocean's worth of water this way before the star ever calmed down. By other estimates, far less. The honest answer is that it depends on how much water the planet started with, how it formed, and whether it migrated inward from a colder birthplace, and we do not know any of those things. This is modelled history, not measured history. But the mechanism is real, and it means the planet may have arrived at the present day already stripped, already dry, already airless. And even setting the violent youth aside, holding an atmosphere against Proxima today is not guaranteed. This star, huddled so close, batters the planet with a stellar wind, a constant gale of charged particles streaming off its surface that may press on Proxima b with a force thousands of times greater than the solar wind presses on Earth. That wind can strip a planet's air from the top, peeling it away over time, especially if the planet has no magnetic field to deflect it. And whether Proxima b has such a shield is, itself, unknown. So you have a planet that may have been scorched dry in its youth and may be having whatever remains slowly scoured off in its old age. One study concluded that under harsh assumptions, an atmosphere could be lost in as little as 10 million years of geological blink. But, and this is the crucial caveat, that the frightening headline always omits that estimate depends enormously on how thick the atmosphere was to begin with, and it is, in the words of the researchers themselves, highly uncertain. A thin skin of air would be stripped fast. A massive one might endure. Volcanoes might resupply from below even as the top erodes. But erosion from above is only half the ledger, and there is a force that could in principle push back from below. Return to that master dial from earlier, the stretch of the orbit, the eccentricity kept alive by Proxima b's sibling worlds. If the orbit is even modestly stretched, then as the planet swings nearer to and farther from its star across each brief orbit, the star's gravity squeezes and releases it, flexing the whole planet like a ball worked in a fist. That flexing is not free. It generates heat deep inside the rock, and that internal heat can drive geology. It can keep the interior molten and restless, and it can feed volcanoes. And volcanoes are not only destroyers, they are also breathers. When a volcanic world erupts, it vents gases from deep within the rock up into the sky. Carbon dioxide, water vapor, sulfur compounds, the raw material of an atmosphere. So a tidally flexed Proxima b could be quietly resupplying its air from beneath, even as the star strips it from above, a planet exhaling from its own interior to replace what the stellar wind tears away. This is exactly why we cannot declare the atmosphere doomed, just because the erosion is fierce. On a geologically alive world, the sky is not a fixed reservoir slowly draining. It is a balance between what is lost at the top and what is belched up from the depths, and which side wins is something we simply cannot calculate without knowing the planet far better than we do. Yet, and this is the cruelty woven through nearly every hopeful thread in this story, the same fire that could refill the sky carries a hidden cost. Too much tidal flexing, too much internal heat, and the planet's interior can be thrown out of the delicate arrangement needed to generate a global magnetic field. The churning that makes a magnetic shield is a fussy thing, and a world overheated by relentless tidal kneading might fail to produce one, or might drive its volcanism into a punishing excess that reshapes the surface faster than anything could settle. So the very stretch of the orbit that might save the atmosphere from below could, at the same time, cost the planet the magnetic shield that would protect that atmosphere from the star's particle storms. Give with one hand, take with the other. The fire that feeds the sky may also strip away its armor, and once again, we are left holding a possibility we cannot yet weigh, on a world we have never truly seen. Picture it as a bathtub, with the drain wide open and the tap barely trickling. If the tub started nearly empty, it is dry within minutes. If it started full, or if the tap runs hard enough, water can stand in it for a very long time even with the drain gaping. Proxima b is a tub whose starting level we never measured and whose tap we cannot see. We know the drain is open. We do not know if the tub is empty. That is the true state of our knowledge, and no amount of confident narration on the internet changes it. Anyone who tells you flatly that Proxima b is airless, or flatly that it is Earth-like, is reading from a script the data has not written. So let us do the honest thing and lay out the possible worlds as a fan of genuine outcomes, each one clearly labelled, and walk through what it would actually mean to stand there. There are 4 broad branches, and they are not 4 flavours of the same planet. They are 4 different planets wearing the same name. The first branch is the airless world. Suppose the youth stripped it, or the wind scoured it, or it never held much air at all. Now that eyeball becomes real in its most merciless form. With no atmosphere to carry heat, the star-facing hemisphere has nowhere to send the energy pouring onto it, and nothing to hold it. The substellar point, that spot of eternal noon, bakes, its surface climbing toward temperatures far above the point where any water would flash instantly to vapor, a dry, blasted, shadowless waste of rock under a motionless red disk. And the night side, receiving no light at all and holding no air to insulate it, radiates its heat straight into space and plunges toward the cold of the void, hundreds of degrees below freezing, a frozen expanse where any gas that wandered over from the dayside would simply freeze solid onto the ground. Between them, a narrow band of twilight where the temperature passes, briefly, through survivable but with no air to breathe, no pressure to keep water liquid, and no shield against the star's radiation. Survivable temperature is a cruel technicality. On an airless Proxima b, a human being could no more live outside than they could on the surface of the moon. Any settlement would be, in every meaningful sense, a spacecraft that happens to be sitting on the ground. This is the bleakest branch, and we cannot rule it out. But, and here is where the story turns, and where the lazy version of this planet's tale gets it wrong. An atmosphere changes everything, and it does not take much of one. This is the second branch, the thin atmosphere world, and it matters enormously, because there is a widespread assumption that a tidally locked planet must have a burning day side and a frozen night side, a dead hemisphere and a habitable ring. Climate models have spent the better part of a decade dismantling that assumption, and the reason is a piece of physics worth understanding, because it is the hinge on which this planet's habitability actually swings. Air moves heat. On Earth, the reason the tropics do not roast and the poles do not freeze into total lifelessness is that our atmosphere and oceans work as a vast central heating loop, a planet-sized radiator circulating warmth from where the sun beats down hardest to where it barely reaches. Winds carry hot air poleward, currents drag warm water thousands of kilometers. The whole system smears the sun's uneven gift across the globe until the difference between the hottest and coldest places is far gentler than the raw sunlight would ever produce. Now put a version of that same machinery on Proxima b. The star may hold the sun frozen over one hemisphere, piling heat onto the day side without pause, but if there is an atmosphere to catch that heat, the winds will do what winds do. They will lift the hot air off the substellar point and carry it around the planet, spilling it across the terminator and out over the dark hemisphere, warming the eternal night from the outside. And crucially, the models show that because Proxima b receives relatively modest starlight in the first place, only about 65% of Earth's you do not need a thick, Earth-like atmosphere to make this work. A comparatively thin one, even a fraction of Earth's pressure, can be enough to move the heat and keep the whole planet from splitting into furnace and freezer. A thin atmosphere is sufficient to distribute heat, precisely because the heat that needs distributing is not that fierce. There is a threat lurking in the thin atmosphere branch though, and it has a name: atmospheric collapse. If the air is too thin to move heat efficiently, then the night side keeps radiating its warmth into space, and keeps getting colder, and eventually it can get so cold that the atmosphere itself begins to freeze. Carbon dioxide is the usual victim. On a night side cold enough, it settles out of the sky and frosts onto the dark ground as dry ice, a permanent snowfall of the very gas that was supposed to be keeping the planet warm. And as the air freezes out onto the night side, the atmosphere thins further, which cripples heat transport further, which freezes out more air a runaway in the wrong direction that can strip the day side of its blanket and leave the planet effectively airless where it counts. Whether Proxima b falls into this trap depends on exactly how much atmosphere it has and what that atmosphere is made of. A little too thin, and it collapses onto the night side. Thick enough, and the circulation holds and the planet stays whole. We are, once again, standing at a fork we cannot yet see the far side of, which brings us to the third branch, and the most hopeful one, the substantial atmosphere world, the version with real air and above all real water. This is the branch the climate modelers have lavished the most attention on, and it is the one that comes closest to the dream, though even here, close to the dream and a second Earth are not the same phrase, and I will not let them blur. Give Proxima b a genuine atmosphere of roughly Earth-like pressure, and give it an ocean, and something remarkable happens in the simulations. Water is an extraordinary mover of heat, far better even than air. A liquid ocean beneath a circulating atmosphere becomes a second, deeper radiator, hauling warmth through its currents from the blazing pupil of the dayside out toward the frozen rim and beyond. In these dynamic ocean models, the brutal contrast of the eyeball softens dramatically. The dayside does not boil, the nightside does not freeze solid. The whole planet is pulled towards something far milder, a world with a warm, open sea directly beneath the motionless sun, ringed by ice further out, but with temperatures across much of the globe that a human being could, in principle, endure. This is the eyeball ocean, and it is worth picturing properly, because it is genuinely beautiful and genuinely strange. Stand at the substellar point of this version of Proxima b, and you are not on scorched rock. You are at the centre of a vast, permanently sunlit sea, the warmest water on the planet, gathered directly under the red eye of the star. Sail outward in any direction and the water cools. The sky's red disk sinks toward the horizon behind you, and eventually you reach a shoreline not of land but of ice, the frozen iris of the eyeball, where the eternal twilight begins. The habitable region of such a world would not be a thin ring at all. It could be a broad, sunlit ocean hemisphere, a whole face of the planet under a still red sun, with liquid water and survivable warmth. The models that produce this outcome are real, published, and taken seriously. But hold the tier in mind. This is a modelled possibility resting on assumed inputs, an assumed atmosphere, an assumed ocean, an assumed water inventory that the violent youth may have already burned away. It is the best case the physics allows. It is not a photograph of anything anyone has seen. And then there is the fourth branch, the reminder that thick atmosphere does not automatically mean gentle world. This is the storm-dominated version. On a planet where the sun is nailed to one spot in the sky, pouring heat relentlessly onto a single patch of ocean or ground, the air above that patch is forever rising, heated, buoyant, climbing, and where air rises endlessly, storms are born. The substellar point of a wet, thick atmosphere, Proxima b, could sit permanently beneath a colossal, churning tower of cloud, a perpetual tempest anchored to the spot directly under the star, wringing out rain that never stops, throwing up a shield of cloud so bright and so thick that it reflects much of the starlight back to space before it ever reaches the surface. That cloud shield is a double-edged thing. It could actually cool the dayside and help stabilize the climate, which some models see as a rescue, but it also means the sunniest place on the planet might be drowned in permanent overcast and lashed by unending storm, while the winds spiraling out from that engine drive fierce, strange weather across the rest of the globe. And if the atmosphere is thick in the wrong way, heavy with carbon dioxide, too good at trapping heat, the whole planet could tip instead toward a suffocating Venus-like greenhouse, the surface pressure crushing, the temperature soaring far past anything life could bear. A thick sky can save a world or smother it, and which one Proxima b would get depends on a chemistry we have not sampled. 4 branches then: the airless corpse, the marginal thin-air world teetering on collapse, the temperate ocean refuge, and the storm-racked or greenhouse-choked thick-air world. Notice what they share and what they do not. They do not share a climate, a temperature, a sky, or a verdict on life. What they share is a single point of ignorance. At their root, we do not know which one is real because we have never measured the one variable that separates them, not the light. The light we know, the air, and every property of the air that matters, whether it exists, how much there is, what it is made of, whether it holds water, whether it moves heat, whether it collapses or storms or soothes, is, as of today, unmeasured. When you hear Earth-like planet in the habitable zone, understand that the phrase is compatible with all 4 of these worlds at once. It is a statement about a location and a mass. It is silent about which of these 4 planets is actually waiting there. This is why I keep refusing the tidy pictures. It is not true that tidal locking guarantees a dead night side. A moving atmosphere can warm it. It is not true that survival would be confined to a thin twilight ring. A real ocean could open up a whole sunlit hemisphere. And it is equally not true that the planet is confirmed to be a mild blue-green haven. It may have lost its water before life on Earth had even begun. The reality that the evidence permits is a fan of radically different worlds, and intellectual honesty means holding all of them open at once, weighing them by physics and admitting that the deciding measurement has not yet been made. That measurement is coming, and it is worth understanding exactly how, because the method is as delicate as the question is enormous. The obvious trick astronomers use on many worlds waiting for a planet to cross in front of its star and reading the starlight that filters through its atmosphere is closed to us here, because, as we established at the very start, Proxima b does not cross its star from our point of view, so we cannot simply catch its air backlit. Instead, the plan is far harder. To separate the planet's own feeble glow, the tiny sliver of red starlight it reflects from the overwhelming glare of the star sitting right beside it, and then to spread that sliver of light into a spectrum and hunt for the fingerprints of specific gases written into it. It means building instruments that can hold a blinding star and a dim planet in the same view and tell their light apart, using both extreme contrast and extraordinarily fine colour resolution at once. Two great efforts are aimed squarely at exactly this. On the ground, an enormous new telescope with a mirror nearly 40 metres across the extremely large telescope, due to open its eye near the end of this decade, may have the sheer light-gathering power and precision to attempt it for a target as close and favourable as Proxima b. And in space, astronomers are designing a future flagship observatory, the Habitable Worlds Observatory, conceived in large part to do precisely this kind of work, to directly image small, potentially temperate planets around nearby stars and read their atmospheres. For once, Proxima b's greatest liability in every other respect, its absurd closeness to a violent star, becomes an asset, because closeness is exactly what makes the planet's faint light barely separable from the glare. The nearest world is, for this one purpose, the most reachable target in the sky. And what would they be looking for? The chemical signatures that might hint at life: oxygen, methane, water vapour, carbon dioxide, and above all, combinations of gases that should not coexist. On a dead world, chemistry settles into a quiet balance. But put oxygen and methane in the same sky together, and you have a puzzle, because those two gases destroy each other quickly. Finding both at once suggests something is constantly replenishing them, and on Earth that something is life. A pairing like that, out of chemical equilibrium, is the kind of clue that would set the whole world of science alight. But here is where I must hold the line one last time, because this is precisely where hope outruns proof. Even a beautiful detection would not be a confirmation of life. It would be a beginning, not an ending. Non-living processes can counterfeit these signals. Recall the very erosion we have been discussing, where the star's ultraviolet light splits water apart and the hydrogen escapes to space. That same process can leave oxygen behind in a planet's air with no life involved at all, a false positive dressed up as a triumph. So a promising signal from Proxima b would launch years of painstaking work to rule out the imposters, to check the context, to ask whether the chemistry could be explained by a merely violent star rather than a living world. We may, within our lifetimes, finally learn which of these 4 planets is actually waiting out there, airless, marginal, temperate, or storm-racked. That alone would be historic. But we detected a gas, and we found life, are separated by a canyon of careful doubt, and anyone who collapses the two is selling certainty the data has not earned. And here is the thread that pulls us, unavoidably, into what comes next. Suppose we get the kindest branch. Suppose Proxima b kept its water and holds a real atmosphere and circulates its heat into that temperate, sunlit ocean world, the best case the models allow. Even then, even in that gentlest of the 4, the story is not safe, because I have spent this entire stretch talking about the atmosphere as though it were the hero of the tale, the thing that redistributes heat and holds water and makes the planet livable. But that same atmosphere, the one thing standing between a human being and the vacuum, sits at the top of the sky fully exposed to a star we have been politely ignoring all this time. A star that does not burn steadily. A star that convulses. Everything I have described, the winds that move the heat, the ocean that warms the night, the air you would breathe floats above a red dwarf capable of erupting, without warning, into flares that hurl radiation and charged particles straight at the very sky, keeping the planet alive. The atmosphere is not just the thing that makes Proxima b habitable, it is the thing that is under siege. And it is time, at last, to look directly at the star doing the besieging. We have been polite to this star for a long while now. We have called it dim, called it cool, called it an ember, and left it burning quietly in the background while we argued about air and heat and water. That politeness ends now, because the single most important thing about Proxima Centauri is not that it is faint, it is that it is furious. In March of 2016, astronomers watching this small red star saw it detonate. Over the space of a few seconds, Proxima's visible light leapt by a factor of about 68, and for a brief window the nearest star to our Sun became just bright enough to glimpse from Earth with the unaided eye under a dark sky. A star normally far too faint to notice without a telescope, briefly flaring into view. This was a superflare, one of the most powerful stellar eruptions ever recorded from Proxima, and it was not a freak once-in-an-era event. It was simply the biggest one anyone happened to be watching at that moment, because when astronomers stare at this star for long stretches, what they find is not calm punctuated by rare violence. They find violence as the baseline. Consider what a recent campaign with the Great Millimeter Telescope Array in the Atacama Desert turned up. Over roughly 50 hours of watching, barely 2 Earth days of observing time, the instrument recorded 463 separate flares, hundreds of eruptions, some lasting only 3 seconds, in the span of a couple of days, and the pattern hidden in those numbers was the truly unsettling part. When the astronomers charted how the flares were distributed by size, they found that the small flares were far more common than the same measurement at other wavelengths had led anyone to expect. The distribution was steep, weighted heavily toward frequent little convulsions. That matters enormously for the planet, because it may mean the total dose of high-energy radiation raining onto Proxima b, especially the extreme ultraviolet light that does the most damage to an atmosphere, is higher than the gentler estimates assumed. This star does not occasionally lose its temper. It seethes constantly with a background crackle of flares and the ever-present threat of a superflare on top. So let us be precise about what a flare actually delivers, because flare sounds like a flash of light, and the reality is far more layered. When Proxima's tangled magnetic field snaps and reconnects, it does not just brighten. It releases energy across the entire spectrum at once, a surge of ultraviolet light, a burst of X-rays, a flood of the extreme ultraviolet that is invisible to us but lethal to molecules, and, often, a blast of charged particles hurled outward at tremendous speed. Some flares are accompanied by coronal mass ejections, great clouds of stellar plasma flung off the star like shrapnel. And remember the geometry from earlier. Proxima b is not standing back at a safe distance like Earth. It is huddled in tight, 1/20th of the Earth-Sun distance, pinned directly in the blast radius. Whatever the star throws, the planet catches, and it catches it square in the face, over and over, for billions of years. Now, here is a distinction the frightening headlines almost always blur, and getting it right is the difference between honesty and fear-mongering. Radiation striking the top of a planet's atmosphere is not the same as radiation reaching the ground. This is crucial. On Earth, our atmosphere and especially our ozone layer absorb the sun's ultraviolet and X-rays high above our heads, so that by the time sunlight reaches the surface, the most dangerous wavelengths have been filtered away. A planet with a substantial atmosphere and an ozone layer could, in principle, do the same for Proxima b, soaking up the worst of even a flare's radiation before it ever touched the surface, so that a person standing on the ground beneath a thick sky might be shielded from the direct blast. So it is simply not true that Proxima's flares would instantly sterilize the surface of any planet with air. If the atmosphere is thick enough, the surface could be protected. But, and this is where the danger reasserts itself, in a subtler, more patient form, the shield is also the target. Every flare that slams into the top of the atmosphere is not just being absorbed harmlessly, it is eroding that atmosphere from above, stripping molecules away into space, driving the slow leak we traced earlier. And the high-energy radiation does something else insidious. It can shatter ozone itself, breaking down the very molecules that protect the surface from ultraviolet light. So even if a given flare does not reach the ground, a barrage of flares over time can thin the atmosphere and chew holes in its ultraviolet shield, so that the next flare reaches a little deeper, and the one after that deeper still, The star is not trying to kill the surface in a single stroke. It is besieging the sky that protects it, year after year, flare after flare, for the entire lifetime of the world. This is the siege I promised you a little while ago, and now you can see its shape. Not one catastrophic blow, but an unrelenting pressure against the one thin layer keeping the planet alive. Could the planet defend itself? On Earth, our deepest protection is invisible. A global magnetic field generated in our molten core that wraps the planet in a shield and deflects the worst of the solar wind and much of the charged particle radiation before it ever reaches the air. If Proxima b had a strong magnetic field of its own, it could hold off the star's particle storms the same way. And you may have seen excited reports suggesting the planet does have such a field. Here we must be careful, because this is a place where the science is real but easily overstated. Astronomers monitoring Proxima at radio wavelengths have detected a signal that appears to pulse roughly in time with the planet's orbit, a tentative sign of what is called magnetic star-planet interaction, the planet electromagnetically ploughing through the star's magnetic field as it circles. It is a genuinely exciting, if still tentative, result, but know what it actually probes. It is evidence about the star's magnetic field, roughly 600 Gauss at the surface, and about the planet moving through it. It is not a confirmed measurement of a protective magnetosphere generated by Proxima b itself. Whether the planet has its own shield remains unknown, and there is even an argument that a slowly rotating, tidally locked world might struggle to generate a strong one. So, we cannot comfort ourselves with a guaranteed magnetic umbrella. The planet may have one, it may not. We do not know, and we should not pretend otherwise. This is the environment, then, that any human presence on Proxima b would have to survive. A world catching constant flares at point-blank range, beneath an atmosphere under permanent erosion, possibly without a magnetic shield, lit by a star that can brighten some 60-fold in seconds without warning. Now let us do the thing this whole journey has been building toward. Let us translate that environment out of the language of astrophysics, and into the language of an ordinary day into what it would actually cost to live there. Begin with the simplest human act imaginable, going outside. On Earth, stepping out your door is free. On Proxima b, it might be the most carefully governed decision of your life, because a superflare can erupt with essentially no warning and reach the planet within minutes. Any time spent on the surface would be time spent gambling against the star. Picture a beach with no shade anywhere, and a sun that can, without notice, blaze to 68 times its brightness, and pour out invisible ultraviolet and X-rays you would not linger. Every excursion outside a shelter would have to be planned around space weather forecasting, around whatever early warning systems the settlement could muster to watch the star for the telltale signs of an impending eruption, and even forecasting only buys minutes. So life on the surface would be lived in a state of permanent readiness, with hardened radiation shelters never more than a short sprint away, and long stretches during the worst of the star's activity, where going outside at all would simply be forbidden. The open sky of this world, the motionless red star we stood beneath earlier, would be beautiful and untrustworthy in equal measure. You would learn never to turn your back on it. Now think about power, because everything else depends on it. On this dim, red world, the obvious energy source is compromised from the start. Sunlight here is thin and mostly infrared, a poor diet for the kind of solar panels that work so well on Earth, and it would vanish entirely on the eternal night side. But the deeper problem is the flares. A powerful stellar eruption, especially one carrying a coronal mass ejection, can induce electrical surges and batter any exposed power system. The same way a great magnetic storm can blow out transformers and fry electronics, a flare could send a surge through a settlement's grid and blow its fuses at the worst possible moment. So the colony's power would have to be both independent of the unreliable starlight and hardened against the star's electrical violence. Buried lines, shielded electronics, deep redundancy, and stored reserves to carry the settlement through the blackouts when the surface systems had to be shut down and sheltered. Every watt would have to be defended. Think about food. We saw earlier that Proxima's deep red, infrared heavy light starves the kind of photosynthesis that Earth's plants evolved to run on. so a settlement could not simply plant fields under the open sky and wait for a harvest. The light is the wrong color, the surface is exposed to radiation, and a single flare could scorch a season's crop. Agriculture would almost certainly have to move indoors and underground, into sealed chambers under artificial grow lights tuned to the wavelengths plants actually need, fed by that same hard-won, hardened power supply. Food would not grow on Proxima b so much as it would be manufactured there. Inside protected rooms, every calorie the output of a machine that must never fail for long. And think about the shelters themselves, because they are the true home. In none of these scenarios, not even the kindest, that temperate ocean world does a person simply live on the surface of Proxima b the way we live on Earth. In the airless or thin air branches, the habitat is a pressurized vessel holding breathable air against a near vacuum, buried or shielded against radiation. A sealed environment as unforgiving of a breach as a submarine is of a crack in its hull. In the temperate branch, with real air outside, you might breathe unaided for a while, but the flares and the ultraviolet would still drive daily life beneath rock, beneath water, beneath shielding, with the surface a place you visit briefly and warily rather than inhabit. Some of the most serious proposals for living on worlds like this are frankly subterranean or underwater settlements dug into the crust or sunk beneath a protective ocean, using meters of rock or water as the shield the planet's magnetic field might not provide. Home, on Proxima b, would mean the inside of something, a shelter, a shell, a protected volume of borrowed Earth-like conditions, maintained by machinery against a world that is forever trying to get in. And that phrase maintained by machinery is the real weight of it, heavier even than any single flare, because the deepest challenge of Proxima b is not one dramatic catastrophe you could brace for and survive. It is not a single killer eruption or one bad day. It is the permanence of the vigilance. It is that the air recyclers must run today and tomorrow and every day after, that the radiation shielding must hold through every flare for 1,000 years, that the power must never fail for longer than the reserves can cover, that the crops must keep growing under their artificial suns, that the seals must stay sealed and the shelters stay whole through every convulsion of a star that will never once fall quiet. Living on Earth, the environment supports you whether or not anyone is paying attention. The air stays breathable and the sky stays safe on its own. Living on Proxima b, the environment is actively hostile, and only unbroken, generation-spanning effort keeps it at bay. It would be like living behind sandbags against a flood that never recedes, where the moment anyone stops stacking, the water comes in. That is not survival as a state you achieve. It is survival as a task you never finish. Now add the final weight, the one that makes all of this so much heavier than any settlement humans have ever built. You would be alone, truly, profoundly alone, in a way no explorer in our history has ever been. Proxima b sits 4.2 light-years from Earth, and nothing, no signal, no message, no cry for help can travel faster than light. Which means that a message sent from the colony to Earth would take more than 4 years to arrive, and any reply would take more than 4 years to come back. A single exchange of question and its answer would consume the better part of a decade. Send word that your reactor is failing, and by the time Earth even hears you, more than 4 years have passed. By the time any advice returns, more than 8. In any real emergency, Earth is not a lifeline. Earth is a distant correspondent reading letters about events that finished half a decade ago, unable to do anything but write back into a past that no longer exists. Every message from home would be, in the most literal sense, a message in a bottle, thrown across an ocean of years, arriving long after the hand that wrote it had moved on. And before we step back to ask what all of this means, there is a quieter toll to name, one that would not announce itself in a single dramatic night, but would accumulate across years and across lifetimes. Even inside the best shielded habitat, on a world lashed by this much high-energy radiation, some dose would always find its way through, and radiation is patient. It does not need to kill you today. It works by accumulation, raising the long odds of cancers and cellular damage across a lifetime of exposure, a background threat that every settler and every physician would have to reckon with as a permanent fact of existence, monitored and managed, but never quite escaped. The occasional great flare would be the emergency. The ceaseless low dose would be the chronic condition. The strange red light would leave its own mark. A body raised under a dim, infrared-heavy sun, or under artificial lamps standing in for a sun the surface cannot safely provide, is a body cut off from the light. Our biology quietly depends on the light that sets our internal clocks, that our skin uses to build the vitamins we need, that our minds seem to lean on for something as basic as mood. None of this is beyond engineering. Lamps can be tuned, supplements can be taken, clocks can be imposed. But every one of those fixes is another system that must be maintained. Another way in which ordinary human wellness on Proxima b would be a manufactured achievement rather than a birthright. And then there are the children. A colony this far away, this isolated, would not be an expedition that comes home. It would be a place where people are born a second, third, 10th generation who never chose the journey, who never saw Earth, and who never could, given a crossing measured in years of light and lifetimes of travel. They would grow up knowing the sun that made their species only as a faint speck in an alien constellation, hearing of oceans and open skies and unshielded afternoons as stories from a world they will never touch. Their entire reality would be the inside of the shelter, the tended air, the tuned light, the wind at the terminator, the two brilliant stars that are not their sun. Whatever home meant to them, it would not be Earth. It would be this, the small, defended, humming pocket of borrowed conditions their ancestors chose to keep alive on a world that never offered to keep them. Sit with what that does to a settlement, psychologically and practically. There is no rescue. There is no resupply that could arrive in time to matter. There is no one to call when the situation exceeds what the colony itself can handle. Whatever goes wrong, the people on Proxima b must solve it themselves, with what they have, in the time they have, because the nearest help is more than 4 years away at the speed of light, and vastly longer at any speed a ship could actually manage. A colony there would not be an outpost of Earth in any meaningful daily sense. It would be a civilization unto itself, a small, sealed, self-repairing human world that must be complete, self-sufficient, and psychologically resilient enough to bear a solitude with no precedent in our species' history. Not the solitude of a lone sailor who will reach port in weeks. The solitude of a people who know that everyone they did not bring with them is unreachably far away, and that the sky above them holds a star that wants their air. And here, only here, at the end of everything, let me step back and say what I think this all means, because we have earned the reflection now. We began with a promise. The nearest star, a planet almost exactly Earth's mass, sitting at the right distance to be warm, close enough to feel reachable, potentially habitable, the headline said, and we heard second Earth, and I understand the pull of that deeply. In a cosmos that is overwhelmingly hostile to us, the idea that there might be another home just 4 light years away, that we are not utterly alone on our single fragile rock, is one of the most consoling thoughts a human being can have. I do not want to take that consolation away for no reason, but I do want to replace the fantasy with something truer, because the truth here is not actually bleaker. It is just more honest, and in its own way more astonishing. Proxima b is not frightening because scientists have proven it to be a dead, sterile world. That is the crucial thing to understand, and it is the opposite of the fear the internet usually sells. We have not confirmed that it is airless. We have not confirmed that it is uninhabitable. For all we know, hidden behind our ignorance, there may be a temperate ocean under that still red sun. Exactly the gentle world the kindest models allow. The fear does not come from certainty that Proxima b is a corpse. The fear comes from the realization that almost every version of it still consistent with the evidence the airless one, the collapsing thin air one, the storm-racked one, and even the temperate ocean one would demand of any human living there. A life of near total dependence, restriction and vigilance far beyond anything ordinary human existence has ever required. It is not the worst case that unsettles. It is that even the best case is so much harder than the word habitable ever let on. Because look at what even the gentlest branch actually offers. Suppose Proxima b kept its water. Suppose it holds a real atmosphere and circulates its heat and opens up that sunlit ocean hemisphere. Even then, you would not walk out under an open blue sky, because the sky is red and the star is treacherous. You would not spread across the whole globe, because habitable ground might be a single sunlit face while the rest lies in ice or storm. You would be geographically restricted, pinned to whatever narrow band of the world the physics allowed. You would not live off the land in any earthly sense, because the light is the wrong color and the surface is exposed, so your food and your air and your safety would all be technologically manufactured and technologically dependent, every day, forever. And you would do all of it more than 4 light years from every other human being who stayed behind, separated from any meaningful help by a gulf that no message can cross in less than 4 years. A temperate Proxima b would still not be a second Earth. It would be a place where humanity had to build, from scratch and defend without pause, a small protected pocket in which human life was merely possible. And that, in the end, is the thing worth carrying away from this whole journey. We tend to imagine that reaching the nearest potentially habitable planet would be a homecoming that we would arrive, step out, breathe the air, and know we had found somewhere the universe had set aside for us. But Proxima b was not set aside for us. Nothing about it was made for our lungs or our crops or our fragile bodies. It is a world of unknown air, huddled against a violent star that never once promised to hold us. So, if we ever reach it, if human beings ever do stand beneath that motionless red disk, it will not mean we found a second home waiting in the dark. It will mean something harder and honestly prouder than that. It will mean we learn to carry our home with us, that we learn to keep a small, sealed, artificial jar of Earth, its air, its water, its warmth, its light alive and intact on the surface of a world that offered us none of those things freely, beside a star that spent every day trying to take them back. Not a second Earth found, a first Earth painstakingly rebuilt and fiercely defended, 4 light years from home. And perhaps that is the real lesson the nearest planet has to teach us, that the galaxy is not dotted with waiting homes, but with worlds that will only ever hold us if we are strong enough and careful enough, and patient enough to build our own shelter and never stop tending it. Proxima b is the closest test of whether we could. And we do not yet know, we genuinely do not yet know what is waiting there under that red and restless sun.